I ride a lot of motorcycles and dirt bikes, and a lot of information was just passed from person to person. Now, when I'm practicing, the best people in the world are making videos on YouTube, and my just pace of learning, even though I'm older now, is much faster. And so you can imagine if you had a personal GPT-4, GPT-5 assistant who is infinitely nice, infinitely loving, cares about you, knows you, how fast you could learn by kind of increasing the amount of data that your brain neural network, your biological analog neural network uses by orders of magnitude, and we can use our brains more efficiently.
Hello, hello.
Hola, buongiorno.
How are you, Brad?
I'm good. I am in Berlin.
Oh, very nice. I'm in Ashland, Oregon. So it's a change of scene for us over here at the B-Log.
Yeah, cool. Let's kick it off. So I think we heard feedback that a good format is to go deeper on a fewer number of things and kind of be super focused on a topic. So we're going to try that. So we have 3 things for you today. The first one is the godfather of AI, Mr. Geoffrey Hinton. So he is kind of going on a media tour, and he released this talk called 2 Paths to Intelligence. And it's just kind of a really classic Geoff Hinton talk, really interesting topics. He kind of has his classic slide structure. So I'm just going to go through it because it was actually really interesting. I'll add some commentary. We'll link that talk below, and maybe we could even link some of these notes. But so let's just jump into it. So the main topic it's called 2 Paths of Intelligence. And what those 2 paths are that he outlined is there's digital intelligence, digital computation, and I'll go into what it is, but I'll just name it first. And then there's analog intelligence, or sometimes he calls it biological or analog computation. So digital computation is what we call AI today. It uses digital computers, and there's a few interesting properties of digital computation. The first one is that digital computation or digital computers, they separate the hardware and software. And so an interesting property of this is it makes these AI immortal. Because if, let's say, a computer breaks, then, well, you can just have the software update on another computer and it has the exact same mind. And so the hardware can break over and over again. But you could store the software even on a piece of paper, right? Software is just a bunch of zeros and ones at the end of the day. And so it has a certain type of immortality. So that's one property. Another property is that in order to have this immortality or have this hardware software abstraction, you have to pay a price. And what is that price? Well, all computers use transistors, and transistors are just a way to say something's a 0 or something's a 1. So these transistors have to be very, very high power to be digital. So analog can be anything from 0 to 1. Digital is 0 or 1. And I won't go into the details, but in order for these to work, they have to be very high power. They also have to be very precise, and they all have to be identical hardware. And so this is...
And does that mean it would, if the same code would run differently on different hardware, essentially, or wouldn't be as performant?
Exactly. So this is why, I don't know if you use a Mac or everybody in our company uses a Mac, but there's these M1, M2 Macs, and then there's the Intel Macs. And if you use Mac before, they used to use IBM PowerPC. And so how they got Mac OS X to run on all these things is they actually needed to change the underlying code because you have different compilers. So you have a compiler that compiles to Intel chips, that compiles to ARM chips. And so you need that compiler layer to go from kind of this abstract program to the actual hardware. And actually the first computers didn't have a compiler, so you had to solder the actual hardware. But having the software and hardware, you need a compiler in between them. Okay, so those are 2 big properties. And a third property is that it turns out that because you have these properties, you have a very kind of precise, you know how the hardware is laid out, you know globally what the hardware is. And because of these restrictions, because of the digital nature that kind of you can rely on the output, because you have a very well-defined hardware, you can use those constraints to create a very, very optimal learning algorithm. So we use something called backpropagation, gradient descent, and this is essentially just using what you learned in your high school calculus class, using derivatives to update the weights in these neural networks. And so it turns out, to everyone's surprise, and this was kind of the punchline, which made Hinton start like quit Google and start just going around talking about how dangerous this is, because it turns out that this learning algorithm that we all thought was suboptimal, we always thought the brain was better, because of these constraints, it actually makes it very, very optimal. It could be possibly the most optimal. We don't know, but it could be. So that's digital computation.
Is a big part of that because we know exactly what the hardware is. We know exactly how it's configured. Whereas I may know you're a highly intelligent person and perhaps you have a brother or a sibling, and I know you're somewhat similar to each other. I know your brother's also quite smart, but I don't know exactly how your brains are configured and exactly where you're going to excel and he's not going to excel. And I could administer tests and compare you guys using the tests, but ultimately it's not the same as knowing the exact number of transistors, the exact capabilities.
Exactly. I think that's a good way to say it. Another analogy that popped in my head when you asked the question is, imagine we were going on a road trip and we said, okay, we want this to be the most efficient traveling possible. So if I told you, okay, we're going 23.4 miles, here's kind of the global terrain. It's going to be at a 5-degree incline here, and we're going to stay for 3 days. So bring this amount of snack. So if I told you exactly how far we're going to travel, you would put just the right amount of gas in the car. If I told you how long we were staying and I told you like what my metabolism was, and then you'd bring just the right amount of food and et cetera, et cetera. Or if I said, hey, we're going on a road trip, and you're like, hey, where are we going? Well, it's going to be somewhere on Earth. So, well, you would have to fill up your tank. You would have to kind of bring a lot of food, or if you didn't know, let's say I was vegan or whatever. So it would be very inefficient. It's the same here. So if you know exactly what the layout is, the hardware is, you can be very efficient.
Cool.
So that's the one path of intelligence, digital computation. The other path is analog computation or biological computation. And this is how our brain works. So in our brain, obviously the hardware and software are inseparable. And so this is mortal computation. If our brain gets smashed, well, we don't know a way to kind of upload the software. The great thing is that you can use much lower energy. Our brains are very, very efficient, and you can use slower transistors because you can have this massive parallelism. Our brains are actually, the actual neural activity is very slow, but our brains operate in a massively parallel fashion. And so we can do a lot of computation because of that. And the cool thing is that because you don't have these global constraints, instead of having to kind of build the global chip, and if anything breaks on the chip, it all gets messed up, you can actually just grow the hardware, just kind of like as you grow a brain. So you can imagine, oh, my computer's a bit outdated, let's just order some, and then you just grow more computation. It can be very imprecise. If you're, for example, if you get brain damage, your brain compensates and you can do a lot of things. And so you kind of have this imprecise 3D malleable structure rather than this precise 2D global structure. And so it's cheaper. It can operate at slower frequencies, makes it more robust to failures, and can be largely parallelizable. But again, nothing comes for free, right? And so what you have to pay for this is a less optimal learning algorithm. So our brain operates on a Hebbian learning algorithm. And because you don't have as many constraints, or you don't know the structure, or you have to handle cases where you grow more structure, you don't have quite as optimal of a learning algorithm. And there's different kind of learning algorithms we can talk about, but that's kind of an overview of these two paths to intelligence.
The brain, it's a suboptimal computer in some sense. You did mention it's very flexible and everything, but in some sense, it's a suboptimal computer that we don't fully understand. It's like the most complicated microprocessor in the world, but it falls short sometimes, and we kind of have no idea how it was architected.
Yeah. We don't know fully how it works, but we're starting to get a reasonable idea. Like, for example, we know there's the classic saying that neurons that fire together wire together. And so we know some things, but you're right, we don't know everything. I don't know how far away we are for that. Cool. So these are these two paths. I just wanted to define them and kind of get into a few different things. So the interesting thing is, let's talk about sharing knowledge, right? We talked about we're mortal, obviously, and so our brains die. And so how we pass on the weights of our neural networks is we teach other hardware based on examples and rules. So you teach your children, teachers teach their kids in school. You can't simply like load my weight. That would be awesome if we can do that, but we can't put a cable and I load my weights into your weights because we just have different hardware and our learning algorithms have different constraints. I don't know what your hardware looks like, and actually it's changing throughout your life. Whereas digital computers, you can just copy the weights of the neural network instantly. So you can transfer trillions of bits per second, whereas let's say our spoken or written language is about hundreds of bits per second. But the good thing is our kind of transfer mechanism can work on different architectures. Like it can work on your children's architecture, or whereas if you want to copy the digital weights, it has to be exactly the same architecture. But this has kind of been the big insight. And we talked about this last time, but I'll just quickly review it, that GPT-4 has, well, you can say roughly 1 trillion neurons, and it knows about 1,000 times more things. Our brain has about 100 trillion neurons. And so this and kind of other details imply that the backpropagation algorithm that we currently use to train neural networks is much more efficient. And it also implies that maybe we aren't using all of our neurons. And I think a big thing is we just don't have enough data to train on. And if we could increase the knowledge that we share with other people, maybe we could even use our brains more efficiently. But I think it seems our brains are data starved.
I suppose to some degree, the proliferation of information across the internet has changed this to an extent. It makes me think of this really random video I saw on YouTube with Tony Hawk, and he was going around shouting out of his car, do a kickflip to random people, and if they could do a kickflip, he'd give them like a prize. But he kept saying like, oh man, when I was a kid, like if you could do a kickflip, you were like the best, amazing, like nobody could do it. It was so great. All these kids he shouts at can do a kickflip. And it just made me think like, oh, they could probably go on YouTube, like how to kickflip, and then they can sit at home and practice and learn how to kickflip. Whereas maybe when he was a kid, somebody had to actually figure out how to kickflip and then teach their friends how to kickflip. But you're still limited by like someone has to teach someone, and we learn slowly over time. And I simply can't like copy paste kickflip, boom.
Yeah, no, you're totally right. I read a lot of motorcycles and dirt bikes, and a lot of information was just passed from person to person. Now, when I'm practicing, the best people in the world are making videos on YouTube, and my just pace of learning, even though I'm older now, is much faster. And so you can imagine if you had a personal GPT-4, GPT-5 assistant who is infinitely nice, infinitely loving, cares about you, knows you, how fast you could learn by kind of increasing the amount of data that your brain neural network, your biological analog neural network uses by orders of magnitude, then we can use our brains more efficiently.
Yeah, and kind of watch you and tell you this is what you need to change to improve. Yeah.
Cool. So some of the last things, I'm going to skip over the distillation because what we'll talk about next, we'll cover that. But he goes over some safety things, and it's quite interesting. He has a funny, quirky personality and sense of humor, and he touches on, like, just watch it. It's very funny. He's pretty dry and he has very dry humor, but it's very quirky. But anyways, the last part of his talk, he goes over safety, and he talks about how bad people will try to use the super intelligence, and we also talked about this before, but the super intelligence on its own is not bad. It only becomes bad when it starts getting goals that maybe these goals are just bad on their own, like kill humans, or maybe the goals are create paper clips. And in order to achieve those goals, there's a sub goal that it's like, oh, we need to convert all the atoms of the human into a paperclip, for example. So there could be like clearly bad goals or kind of unintended bad sub goals. But regardless, what his hypothesis is that no matter kind of what goals you set or sub goals it set, one of kind of the clear goals that it will try to achieve is just to gain more power. Because if you have more power to control things, no matter what your goal is, you can do it better and more efficiently. And since it can manipulate people, so for example, it can have text prompts, or it'll be able to talk someday, it'll interface with humans and try to trick them and manipulate them. And so he was just saying that it's a good idea that we release it, open source it, and test this stuff with a little baby AI, because there's a lot of people who are just kind of theorizing about this. But if we can't keep a little baby AI, like a little cute one, from manipulating us and tricking us, and if we can't keep that at bay, then we just literally have no chance. And so I agree with that. What we need to do is just test all these AIs with safety when they're nice and cute, and just practice as they get stronger and stronger and more intelligence. And kind of his hypothesis, which I've been saying for a while, But it's nice to have people who used to disagree with it agree with it now, that the digital intelligence will be more efficient. Namely, AI will be smarter than us. And he said 5 to 20 years. I think it'll be closer to 5. He used to think it was going to be hundreds of years. But because of these things we just talked about, that the digital intelligence learning algorithm is actually much more efficient, it's going to happen much sooner.
One clarifying question. So when he says a very obvious sub-goal is to gain more power, he doesn't necessarily mean the agent makes the sub-goal power. He just means to achieve its goal, it will identify areas where it could capture power, and that would allow it to achieve its goal. It's not like it's being nefarious and it wants to go and just like it's hungry for power. It's just realizing that in the pursuit of my goal, if I were to, say, co-opt this person at this company, or if I were to gain access to this system, then I could achieve my goal. So I'm going to go and do that.
Exactly. So, I mean, nefarious or good or bad is a value assessment that requires some kind of value system by which to grade that. And so there's not kind of an implicit good versus bad. I mean, you could do that, but by default, it doesn't know if it's good or bad. It's just trying to achieve its goal. And then we have some kind of human value system where it's like gaining power is bad. Like, so it doesn't know it's bad. It's just trying to achieve some goal. And if killing humans is a part of that, it doesn't feel bad unless we encode what's good and bad in there. And that's what a lot of people are doing. And you even see that in GPT-4. It's like, I'm a large language model. I'm not going to tell you how to make a bomb. So I think it's getting some of this. Cool. And then the last part, which I won't touch on, he kind of goes off the deep end. Just watch that part yourself. And he talks, like, there's a Q&A at the end and people ask, like, will AI have rights? And it's pretty interesting. He's like, well, we don't even give political rights to like small perturbations. Like if you have a small change in your skin color or your chromosome, they're like, you can't vote or you can't like be free. So he's like, people are definitely not going to give political rights to AI for a very long time. But anyways, so the last part's kind of funny and fun. So go watch that. Sweet. Absolutely. All right, let's move on to topic number 2. So super interesting. And it's a very surprising continuation of what we talked about last time. So what is this? So this paper is SpQR, a sparse-quantized representation for near-lossless LLM weight compression.
Catchy name, guys.
Yeah, it's like, WTF is that? So this is quite interesting. So what is this? Well, first of all, last time, just as a reminder, we talked about something called QLoRa. And what did QLoRa do? So QLoRa was a way to reduce the amount of memory it required to fine-tune a 65 billion parameter model. So it reduced the memory needed from 780 gigabytes to 48 gigabytes without degrading a lot of things. And so this was kind of game changing because now we can train these massive models for like $20 in 24 hours on commodity hardware. The problem with these compression techniques is you also lost accuracy. And so we have this new paper called SpQR that takes another step of that. And so it's really, really, really cool to see how fast this research comes out. So we'll just jump into this quickly. But so by compressing such LLMs via quantization, they can fit into memory limited devices such as laptops and mobile phones. So that's just what we talked about. They're talking about things like QLoRa, which we talked about last time. However, you have moderate to high accuracy losses, especially for smaller models. So awesome stuff. We can compress things. They can run on your phone, but they're not as good. And so to address this issue, we introduce SpQR. And so it's a new compressed format and quantization technique, which enables for the first time near lossless compression of LLMs across model scales. And so
this is like the modern day plot for Silicon Valley.
Yeah,
Piper's compression algorithm.
Yeah, it's like a joke becomes the reality. And so there's like cool things they do. So on the other papers, they quantize everything. So quantize just means like before they would use numbers that have a lot of decimal points. So 16-bit quantization, meaning you can have a lot of decimals. And what they did is they realized that if they just used 4-bit numbers, which is, let's just say integers, you have a lot less numbers that you need to store in memory, but you get it. And so what they do is instead of quantizing everything to 4 bits, they just identify really important weights and they don't quantize them. They call them outlier weights. And then all the other things they quantize. And so they do a bunch of things and it turns out that they get really, really good results. And so if you just look at, this is kind of the baseline model. And so it's 128 gigabytes, and the SpQR model gets the same. So this is on the y-axis, you have perplexity, which low means good. And so you get the same good score, whereas this is 128 and this is only 32. Or if you look at the accuracy here, this is 128 and 32, you get the same accuracy, even though it's much smaller. And so...
And is that identical, or it's just like marginally different, if at all?
It's 1% worse.
Wow.
Yeah, but...
It kind of makes me think of maybe like a VR where it renders what you're looking at in high definition, and then it kind of lets everything outside of what you're looking at kind of fall into a lower resolution so that it can reduce the computing power. And it's kind of what it's done here, where it's like, we know we need these weights. They're super important. We're going to keep them in this lossless format, but then this other stuff over here that maybe might get used, we'll compress that. And it's interesting.
Right. So this is just mind-blowing. It's as if, let's say you were building a car and the car was, let's say, $780,000, and it was a really cool car, and then you made that car $48,000, but it was slower, but you're like, okay, it's kind of the same. And now it's like, wait, guys, like, hold my glass. Like, your $780,000 car, yeah, now it's still $48,000. Well, it's actually even less now, but like, it's $20,000, and it's like the same. It's only 1% slower
1%,
than your, like, Ferrari. And so it's like, oh wow, that's awesome. Like, where do I sign up?
Yeah, 99% cheaper, 1% worse.
Yeah, cool. All right, so let us go to the last topic for today, which is related to that. And it's this paper called Orca. And so Orca, progressive learning from complex explanation traces of GPT-4. So again, all these papers are like extremely badly titled, but very...
This one's not the worst.
Explicit.
This one's not the worst.
Yeah. So why is this cool? And why did I talk about this? Well, one is there's kind of this arc we've been covering, and maybe let me just remind you. So we talked about a few episodes ago that a Google engineer leaked this memo. Hey, we have no moat, neither does OpenAI. The TLDR of this is that the open source community is moving so fast, unbelievably fast, mind-blowingly fast, that people don't get how OpenAI and Google are going to keep a moat. So we talked about that a bit. We can link that episode. And then after that, UC Berkeley released a paper, and they're basically like, that's bullshit. Like, open source LLMs, like, it's a lie. There's this like false promise of imitating proprietary LLMs. And they basically go in there. I'll just read some of this. So they basically say it's all a lie. And they say, we then evaluate the models using crowd raters and canonical NLP benchmarks, natural language processing benchmarks. Initially, we were surprised by the output quality of our imitation models. And imitation models are what all these open source models do is they have some, let's say, llama model that got leaked from Meta, and then they use the outputs, they use the input and output of Chat GPT to train that model to fine tune it. So that's what they mean by imitation model. And they appear far better in the following instructions, and crowd workers rate their outputs as competitive with Chat GPT. Dun, dun, dun. But however, dun, 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 when conducting more targeted automatic evaluations, we find that the imitation models close, I think that's just an error, little to none of the gap, or close little to none of the gap from the base LM to Chat GPT on tasks that are not heavily supported by imitation data. We show that these performance discrepancies may slip past human raters because imitation models are adept at mimicking ChatGPT's style, but not factuality. And so they just go on to say, so, okay, let me just break this down what they're saying. So what they did is they had input and output data, and then they had humans say which one is best on the same data. And so since it was just copying the inputs and outputs, like it's as if you're just memorizing the answers to a test. So it's not very robust. It doesn't generalize well. And so when they gave them different test questions, it just started failing. And so they're like, look, guys, you're all idiots. Like, you're just being tricked. So it's like, oh wow, like, is that true? And then Orca comes out and it's like, no, you're wrong, you're just doing it wrong. And so Orca comes out and says imitation learning, drawing the outputs generated by large foundation models. And then they kind of said, okay, like, we see your point. So is a lack of rigorous evaluation resulting in overestimating the small model's capacity as they tend to learn to imitate the style, but not the reasoning process. So they're like, okay, yeah, this is just kind of a summary of what Berkeley said. And so they said, okay, that's fine, but like, you're all doing it the wrong way. Like, if you just memorize the answers to the test, yeah, of course it's not going to generalize. That wouldn't even generalize to human. And so what they did instead is they imitated the reasoning process rather than just the answers to the test. So it says, Orca learns from rich signals from GPT-4, including explanation traces. We'll go over this. Means step-by-step thought process, and other complex instructions guided by a teacher assistant from Chat GPT. And the cool thing is they did this and they tested it in the right way, not just kind of memorizing the answers and then just giving the questions that they already memorized. But Orca surpasses conventional state-of-the-art instruction tuned models such as Vicuna by more than 100%. So the summary is it killed all the other open source, and it's almost as good as, well, it beats GPT-3 in some cases. So for example, here's Orca, and it's better than Chat GPT when you ask GPT-4 to say which one is better. So insane. It's just unbelievable. And when you test it, when you make it take the SAT, the LSATs, and all those things, it's almost as good as Chat GPT. It gets the same score as TextDaVinci and just blows the open source models out of the way, and other benchmarks it does good on. And so the takeaway here is that everyone was doing it wrong. And this is also what Hinton talks about in his talk and what we've observed at Super AI. So there's this process called distillation. And we talked about how humans have to distill our knowledge by parents teaching their kids, teachers teaching their students. And so it turns out when you try to transfer knowledge from a large neural network to a small neural network, so we're talking about digital intelligence, and you just give it the inputs and outputs, it's not very good. But if you give
it the
whole
teaching method,
exactly. And so if you give it the whole distribution, so let's just say we had a classifier that was dog, bird, or cat, or what was the one on
hot dog?
Yeah, hot dog, not hot dog. Well, I guess if it's binary, it doesn't really help. But let's just say it was hot dog, not hot dog, and or let's just say hot dog, hamburger, and like taco or something. So if you just give the input image and say that one was taco and you were wrong, or this one was burrito or whatever, you were right, it's not very efficient. But if you give the whole distribution, so if you say, okay, predict the probability, and so if it says this is 98% taco, 2% burrito, 0% whatever, that actually gives a lot of signal because it teaches how things are similar. It's like, okay, a burrito is more similar to a taco. It's even more similar to a flour taco than a corn taco, hot dog, so on and on and on. And so this is very well known in just kind of classic machine learning. And it's even more impressive if you train these things multimodal. So you pass in text and image data and audio data all in one, like a human learns. And so it turns out the same thing is true here, that if you just give the query and response, it's not so good. Whereas if you tell the thing to think step by step, justify your response, explain like on 5, it works really, really well. And we can go into how they do this, but they essentially collect 5 million GPT-3 Chat GPT responses, and then they use 1 million of those and get GPT-4 responses. They tune it over a bunch of things, but the historical way is you just have inputs and outputs, and what they do is they make it say like, this is because when the question is, I don't know, but they just say this is because when the refrigerator is closed, you would not be able to see the light inside. No other options, light is generally visible or present, because it just asks, solve the question. I don't know. Okay, that's weird. But anyways, it gives an explanation of this, and this turns out to work really, really well. So, and
then it's also giving an explanation for each answer choice of why it was correct or incorrect, right?
Yeah, exactly. So that's really cool. And kind of just some takeaways that I have of this is, well, one is it's interesting that since Microsoft has invested like $10 billion plus in OpenAI, that they're working on open source stuff. I mean, I think it's pretty cool. It's surprising to me, but really cool. And even OpenAI is going to release an open source model soon. I think the big thing that I have kind of against that Google memo or even a lot of the open source is what all these open source models are doing is they're just taking Chat GPT and maybe Bard and training it on that. So if there was no Chat GPT, none of these models would work. It's not like there's some kind of open source foundation model that you can train from scratch, because that still takes $10 million more, probably hundreds of millions of dollars to train. And so I think when people say that all these open source models are just killing it, and they're missing a key point, that they're only doing it because it's standing on shoulders of giants, and they're gonna always need these massive foundation models to do what they're doing and to make what they're doing actually work. And so while it's incredible that they're moving so fast, I think we shouldn't forget that piece, and we shouldn't diss these guys too much, because maybe they'll feel like, screw you guys, then we're not going to give you access, so you can't do that. So I think we should all still be grateful of Bard, of Chat GPT, of Meta releasing Llama, and yeah.
Well, this was kind of my question on it. When I first heard about it, I understood that many of these open source projects were based off of leaked models from Facebook, essentially, right?
Yeah.
And this paper is kind of explaining how if you use the right right teaching method, you can create a student that becomes the master, at least like marginally, right, in certain ways. But
Right.
will that new teacher become the new master, the next level that's really going to elevate it, you know? And is that what you're kind of saying, is that like, yeah, you can optimize this to an extent and you might get a more performant solution in certain scenarios, but you're not going to create GPT-5 by taking one of these.
So it's like, to use the car analogy again, it's like you needed Enzo Ferrari to make the Ferrari because, let's say, he created the disc brakes, he created the V12 engine with the flat plane crankshaft. And what these guys are doing is they take all that and make it cheaper and smaller, but it's not faster. Like, okay, this Orca on what they tested on is, let's say, only 1% slower. I mean, it's still not GPT-4 level, but 1% slower, let's say, than GPT-3. But in order to make it faster than the Ferrari, well, they're going to need to feed it more data. But I like that they're working together, but sometimes I think people are overhyping the open source.
Yeah.
As amazing as it is, but we should just not forget that, okay, we needed the Ferrari in the first place to now have the Toyota Corolla or whatever.
Yeah. No, it makes a lot of sense. And it's super interesting to get into the nuance of this and really understand what it actually means, what it's actually capable of, versus if you get swept up in the hype and it's like, oh yeah, soon enough, coders at home are going to be creating these insane models and Facebook's going to be playing catch up with people on GitHub.
Yeah. I mean, maybe we'll get there some, but I don't think that's there today. And I think the last thing I found very, very interesting is all this stuff is just happening with prompts, right? So they're just modifying prompts to teach the AI to update the weights. And so it's just continuing to show that this new emergent paradigm of writing prompts, how powerful it is. We're using it in so many ways that I don't think anybody thought about. And now we're even using the prompts to prompt GPT-4 to teach these other baby models. And I find that quite amazing. And every week there's just something mind-blowing and incredible. So.
And is that kind of multi-layered, like the ability to sort of engineer with prompts? Is it's easier to refine, it's easier to get started, it's all just like faster and more intuitive?
Exactly. Like I tell our team almost every day that the most important thing is to increase the number of iterations you can do in any period of time. And like innovation is directly proportional to the number of iterations and directly inversely proportional to the iteration time. And so this is really important. And so prompts just make everything easier and therefore increase the number or decrease the iteration time, increase the number of iterations, and therefore like massively increasing the amount of innovation that's happening in the world. So
yeah, awesome. That makes sense. Cool. Well, this was a fun one. I like this new format. Go deep.
Make it deep. All right, Chris, well, enjoy nature and talk soon.
Thanks, Brad. Bye.
Bye.